Okay, so in this second video for the equations of motion, what I'm going to do is I'm just going to solve several more examples so that you guys get proficient at solving them. In class, we're going to do lots and lots and lots of examples from your homework study packet. And obviously, as we do more examples, they'll get more and more complicated. But don't be daunted by the complexity of these problems. The same basic format strategy for solving problem remains. What you want to do is make a SUVOT table, write down what you know, what you don't know, and then choose the appropriate equation of motion. So let's get started with the next example. Okay, pause the video and read this one. Okay, so a car has initial velocity of positive 5 meters per second. When its displacement has increased by 20 meters, its velocity is now 7 meters per second. Okay, so it's speeding up. What's the acceleration? Okay, very easy if you remember the whole SUVOT process. Okay, so here's my SUVOT table. Displacement's positive 20. My initial velocity is positive 5. My final velocity is positive 7, okay? And I'm asked to find the acceleration. So based on this, which of the four motion kinematics equations would you use to most easily do this problem, okay? I would use v squared equals u squared plus 2as. And when I do, I get an acceleration of 0.6 meters per second squared. So here's my work. Remember, the positives and the negatives are super important, okay? All right. How about example 5? In this one, a body has an initial velocity of 4 meters per second and a velocity of 12 meters per second after 6 seconds. So clearly it's accelerating. What displacement did the body cover in this 6 seconds? Okay, getting a little more complicated. Here's my SUVOT table. Initial velocity, positive 4. Final velocity, positive 12 times 6. In this case, I'm asked to find the displacement, so I have a question mark there. And I used S equals V plus U times T over 2, and I got 48 meters. Again, you can probably come up with another way to do these problems. And in fact, maybe if you want to in class, if you want to see me work these problems using another method, I can. Often another method involves maybe using two kinematics equations, using the result of one application of a kinematics equation and plugging that into another equation, possibly. But we can do that if you guys want to. Just let me know during class, okay? All right, here's our next example. Read this one. Try it yourself. Okay, so two balls start out moving to the right with constant velocities of 5 meters per second and 4 meters per second. The slow ball starts first and the other 4 seconds later. So clearly the faster ball will catch up with the slower ball. How far from the starting position are they when they meet? Great question. You might want to draw yourself a little picture too in order for you to picture exactly what's happening. So what I've done here is I've made a SUVOT table for each of these rolling balls, okay? And I'm calling the displacement of the slow ball S1 and the displacement of the fast ball S2, okay? And really what I should have done here is I should have called this U1 and V1 and U2 and V2, okay? That's probably what I should have done. In this case, I don't care about the accelerations, all right? Because the acceleration, well, actually the accelerations are 0, so I could actually write that in, although that's not really important, obviously, okay? Okay, so here's the example where I'm going to have to be a little more savvy in terms of my problem solving, okay? The two displacements are equal when they meet, obviously, right? Okay, so when S1 equals S2 is when they meet, right? How far from the starting position are they when this happens, okay? Now, generally S equals T over 2 times V plus U, okay? So I'm doing this expression right here is S2, this is for the slow ball, or sorry, for the fast ball. This expression right here is for the slow ball, S1. And all I do is I now solve for T. When I solve for T, this algebra should be really simple for you guys. If you're having trouble with the algebra, you should come see me or just brush up your algebra. I expect this to not be a problem for any of you. I get 20 seconds is when they meet. Okay, well now great. One thing I didn't mention, notice how I have this time right here as being t minus 4, okay? You might want to pause the video and think about why I put t minus 4 there. That's actually crucial. That's something I kind of glossed over. I didn't even mention that. That t minus 4 ends up becoming t in the second application of the kinematics equation for S2 or the fastball, okay? All right, so at 20 seconds, then it becomes very simple. You can plug this into either equation you wish, okay? Either way you do it, you get S1 equals S2, which is positive 80 meters. So at positive 80 meters is when they meet. One's catching up with the other. How cool are these kinematics equations? How else would you do these problems? Otherwise, it'd be really, really complicated to solve them, okay? All right, next example. Try this one. Okay, a mass is thrown upwards with an initial velocity of 30 meters per second. A second mass is dropped from directly above 60 meters above the first mass. And 5 seconds later, where do they meet and how high is the point where they meet? Okay? All right, so again, I'm making a SUVAT table for mass 1 and mass 2. Okay? Again, for mass 1, I'm calling it S1, U1, V1, and T I'm just calling T1. I guess I can call it T1 right here. Okay, for S2, I have that, this is interesting, S2 is S1 plus 60 because it tells us that mass 2 starts off 60 meters above where the first mass started off, okay? Its initial velocity is 0 because it's being dropped, okay? In both cases, the acceleration is negative 9.81 meters per second squared, of course, because we're dealing with vertical motion in a straight line where the influence of gravity, where things are moving at acceleration due to gravity, okay? And notice that I have for T2, I have that T2 is T1 minus 0.5 because of the half a second time difference, okay? All right, they meet again when S1 equals S2, okay? So I'm using this equation of motion, and what I do is I solve for T. Look at my math here, make sure that you get this, okay? I get that they meet at 2.34 seconds, okay? And that's at a height of 43.3 meters. Okay, so make sure that you understand this solution. It's getting more and more complicated. Okay. Okay. Next example: a ball is dropped from a height of 20 meters. 1 second later, a second ball is thrown vertically downwards. The two balls arrive on the ground at the same time. What must have been the initial velocity of the second ball? I just want to point out here that with these kinematic problems, we always neglect air resistance, frictional forces, okay? Otherwise, the kinematics equations don't work, all right? Okay, so again, here's my little diagram over here. I have SUVAT tables for ball number 1 and ball number 2, okay? And really what we're asking, okay, we're actually asking for U2 here, the initial velocity of the second ball, okay? First thing I want to do is I want to solve for T, okay? I got T is 2.02 seconds, and then we find the initial velocity of ball number 2 using this particular T1, noting that T2 is T1 minus 1 because it was 1 second later, and I got 14.6 meters per second, okay? All right, so remember, the second ball is catching up with the first ball, and they both hit the ground at the same time, okay? All right, another example, okay? This example number 9 is actually a two-part question. It's this slide and the next slide. Go ahead. This is the most complicated question we will do with kinematics equations. Go ahead and read it and try to solve it carefully on your own before you hit the play button again. Okay, so I have a hot air balloon rising vertically at a constant speed of 5 meters per second. Sandbag is released, okay? The sandbag is going upwards also at 5 meters per second, and it hits the ground 12 seconds later. Assuming the balloon's velocity increases to 5.5 meters per second after releasing the sandbag. Okay, so with what speed does the sandbag hit the ground? This is a fairly easy, part A is fairly easy, okay? For the sandbag, I've made a SUVAT table. Here's the initial velocity of the sandbag. It's going up at 5 meters per second, okay? We're asked to find V. A is negative 9.8 meters per second, and T, that's crucial, it hits the ground 12 seconds later. This is a very simple application of V equals U plus AT to get negative 113 meters per second, okay? How high was the balloon when the sandbag was released, okay? Well, we have tons of information here. We now have V as one of our variables in my SUVAT table. Probably simplest just to use T over 2 times V plus U to get 650 meters, okay? Okay, now C, this is the interesting one, okay? What's the relative velocity of the sandbag with respect to the balloon 6 seconds after it dropped? Now, it takes 12 seconds for it to hit the ground, so at 6 seconds, it's obviously well in midair, okay? Now, for the sandbag, in this case,
there's a new SUBOT table where I've changed my time to be 6 seconds from 12 seconds. Okay, and I then find the velocity of the sandbag after 6 seconds is negative 53.9. Now, here's my reasoning for this one. Since the balloon has velocity 5.5 meters per second at 6 seconds, okay, it follows that the relative velocity between them would be the addition of 5.5 and 53.9 because they're moving in different directions. Remember, if you have a motion detector on a cart and the other cart is moving away from it with the paper reflecting the ultrasonic beam or back to the motion detector, the relative velocity between them is additive, okay? So I got 54.9 meters per second because they're moving away from one another at this rate.